Welcome to this last series of lectures on approximation algorithms. So what did we see so far? Well, we started by giving some basic definitions of approximation ratio and so on. Then we looked at an example, load balancing, and then we looked at LP relaxation, which is a very nice and general technique to obtain approximation algorithms. Our last series of lessons is going to be on so-called polynomial time approximation schemes. So, I hope you remember the basic definition of a row approximation algorithm. It's an algorithm that, for any possible problem instance I, computes a solution which, for minimization problems, is at most row times the value of an optimal solution. Obviously, the closer row is to 1, the closer we get to the optimal solution. Right, so we would really like to get something very close to row equals 1. So the main question is, how close to 1 can we actually get? Well, that depends on the problem. For instance, if you look at the vertex cover problem, we gave a 2 approximation algorithm for that. But actually it turns out that maybe it would be possible to do a little bit better, although nobody has come up with a better algorithm so far, but at least we know that you cannot do better than getting roughly a 1.36 approximation algorithm. So in particular, you cannot get arbitrarily close to 1. For some other problems, however, we can get arbitrarily close to 1. In other words, if you tell me I want a 1.1 approximation, then I say, okay, here you have a scheme that gives a 1.1 approximation. If you say, I want a 1.01 approximation, I can also do it. Okay, so let's see how that works, and let's try to define this a little bit more formally. So a polynomial time approximation scheme is, well, an algorithm that takes, of course, an input instance as input, but it also gets as input a second parameter, which is some value epsilon greater than 0. Okay? And using this epsilon, the user can control how close to the optimal solution the solution computed by the algorithm is going to be. Okay, so more formally, when is this algorithm ALG with these 2 parameters, input and epsilon, a polynomial time approximation scheme, or PTAS as we usually say for short? Well, first of all, the approximation ratio has to be 1 plus epsilon. Okay, so the value computed by our algorithm, so ALG of I and epsilon, is at most 1 plus epsilon times opt for a minimization problem. Secondly, as with all approximation algorithms, the running time should be polynomial. Okay, polynomial in the size of the input. So let's look at this a little bit more closely, because the running time now not only depends on the input size, it actually also depends on this parameter epsilon, right? Which is what you expect, because, well, if you want to get something which is much closer to the optimal solution, somehow you have to pay. And in this case, it means you have to pay in terms of running time. The smaller you make epsilon, the slower your algorithm will be. So let's look a little bit at this dependency on epsilon. So here you see various possible running times, and as you see, if I denote the size of the input by n, then the running time is a function of this n, and the dependency on this n should be polynomial, but it also depends on this epsilon. Okay, note that the dependency on n, the size of the input, should be polynomial. So something like you see here, where there's a 2 to the power n, which is exponential in n, is not allowed. Okay, so these 3 running times, they are simply polynomial in n, and so they are fine. So what you also see, if you look at the dependency on epsilon, these 3 examples, they're sort of 2 different categories. The first example, the running time is not only polynomial in n, but also the dependency on 1 over epsilon, that dependency is also polynomial. Okay. The second and third example of running time you see, there the dependency on 1 over epsilon is not polynomial, it's exponential. Well, obviously, it's nice if not only the dependency on n is polynomial, but also the dependency on 1 over epsilon. So for these polynomial time approximation schemes where also the dependency on 1 over epsilon is polynomial, there's a special name, and they're called fully polynomial time approximation schemes, or in other words, F beta cis. Okay, so this is the basic definition for minimization problems. Well, I guess you could probably already come up yourself with how to adapt this definition for maximization problems. Okay, for maximization, it simply means that the approximation ratio is now not that we have that the solution is at most 1 plus epsilon times opt, but it should be at least 1 minus epsilon times opt. Right? Again, we want to get arbitrarily close to approximation ratio 1, and in this case, that means that you get this 1 minus epsilon. Okay, so what we're going to do in the next lessons is we're going to look at an example of a polynomial time approximation scheme, and this example is going to be for the knapsack problem. And the nice thing of this example will be that it uses a general technique to obtain a p-TAS, to obtain a polynomial time approximation scheme, and this technique can also be applied to different problems. It does not only apply to the knapsack problem.